Count it.
So I would like to invite Mr. Habib Mazharimousavi to give his speech about why neuron fibers do not buckle.
I don't think so. But my PowerPoint was okay. Before I leave the room, something happened anyway. So
You got virus.
yeah, these are not viruses. In fact, it's neuron cells. Yeah. So thank you very much. I'm going to talk about my talk is a kind of application of what Mr. Daniel and Niloufar discussed in last two presentations. Okay, the question is simple: why neuron fibers do not buckle? So I think everybody knows what is buckling, and if you have a solid beam and you just apply non-axial forces, you will see that it starts to bend, and in some certain case, it starts to show buckling. So, what
do you mean by buckling?
buckling? If I have a small
Mechanical engineers.
wire here, yes, I can show you here.
Which one?
Okay, if I'm not going to destroy this. So when you, this is not, of course, a solid rigid stuff, but when you bend it, you see the surface of this wire is smooth, in mathematical language, differentiable manifold. But when you pass to certain, bending curvature, you see here, you will see the surface is not anymore smooth, and you see the points which we say it's Gaussian curvature is not finite.
There
So
is no derivative.
Yes, it's not differentiable at points.
You make it cusp.
Yes, something like cusp, or and we also call it, let's call it not differentiable manifold at that point. So why we know these neuron fibers, they do not buckle? In fact, if you know the structure of neuron cells and their function and how they do their function, we see having buckle will interrupt their, what they're going to do. So we go through, and then we will see if there is such buckling, if there is, what would happen. So this is the outline of my talk. First, of course, we have people from biology. I'm not biologist, so but I have to introduce what are these things we are discussing. And this is just a model, as I said. So I introduce the neuron cell. Mainly, my concentration is on axon, part of the neuron cell, which is responsible to take the signals through the body. And then next, I will give its mathematical model, how we. Then through the model I give, we will find out why how they do not buckle. And after that, if they do not buckle while they are bending, so what kind of curve they will choose in their bending. So this will be the ultimate place I will go. So the next few slides I'm going to show you, most probably Messiah will like much, and you also, those biologists, they love it. But anyway, so this is our nerve system. So we have, everybody knows, of course, just to remind you, we have the main, our brain and the spinal cord, and the other, these are this total structure. And as you see, these fibers, if we call them, made of, their bases are, of course, neurons. They go through all single points on our body, inside our body, everywhere. So they are like kind of wiring our entire body. So this picture also shows that the fibers, which I'm going to talk, they are really like a fiber. They are very long. Of course, with very complicated structure. So these are other form of our nerve system. Nerve system, including the brain and the other, their basis is a cell called neuron. We have different types of neurons, but mainly we can discuss about these three forms. The main one, which takes the signal from the receptors, from the let's say sensory cells. These are what you see here. We have also cells, neuron cells, which they work kind of interneuron, let's say, cells. They are between neurons. And we have also motor neuron, which takes the message from the brain to muscle or wherever it is needed. So the structure, they are more or less the same. The only difference is the length, which they may be different. Some of them, they are, in fact, the main structure of a neuron cell, including all these three, the cell body is the structure which decides what to do with the messages. And in addition to that, there is a long fiber, which is called axon, which is in fact my concentration. Some cells, I mean neurons, they have axon naked to the outer medium, but some of them are like retic wire. They are isolated by myelin. So both of them may be part of our study. And the length of these neuron cells, especially the axon, which is the tail of, let's say, neuron cells. In fact, axon is the extension of the cell body itself. Even the cytoplasm of cell body and axon, 97% are the same, although they call it axoplasm. But due to, as I say, it's the extension of that. And but the length of this axon, sometimes it comes to 1 meter. You see, this is the longest axon or cell, neuron cell in our body. This is, in fact, the sciatic cell nerve. So, although this is not a single axon, they are bunched together by fat or other, let's say, cells. But the fact is, one single axon takes the message from the toe, our toe, to the the lower part of our spinal cord. So, in some sense, they are really wires. So, if they are so long, and they also pass through very complicated passages, so they may also have some points which they bend more than they may be able to bear them. So that is the question which I have asked, whether in those points which, due to the structure of our body, these fibers, they should bend, will they buckle over there or not? So that's the question. And also, these are the neuron cells in our body, but in our brain, which of course they are shorter, we have something 10 to the power 11 neuron cells in our body. So each of them something 10 to the power 5 connection with the other. So very complicated, structure, and we cannot expect all of them go straight. That is not possible, even if we just look at it statistically.
Our body is our daily universe.
It's bigger than our universe, in fact. Yesterday you were talking about everybody may have his own universe. We have already our universe, even more complicated what you told. So now we just ask one simple question about the universe sphere, and this is the schematic way of how our nerve system works. Of course, you are familiar. These blues, they take the signal from the sensory cell to our spinal cord, and from there, using another internal also to our brain, and then the appropriate message comes to the vessels what to do. In this case, because of the hot water, you have to contract your hand. So overall, just as of your information, the speed of these signals, these are electrochemical signals, from 0.6 meter per second up to some 100 meter per second. They may vary. It depends on the size of the axon and also the structure, whether they have myelin or not. Anyway, and this is also a better look at the axon. And as you see here, axon is covered by myelin. It's like plastic to isolate the wire from outside. But between this is not exactly as we put our wire. What we see here, we have some nodes. Of course, this is just for those that are myelin. So if they are not, it is exposed to outside. But here we have some nodes which they exchange the ions, as our friend in the morning he said. Anyway, our main concentration is this axon. So even here in this picture, we see that this myelin cell applies continuous force on some part of this axon, which we were thinking how force may change. And by the way, axon also consists of bilayer, and as its bilayer goes to the cell itself. So it means that we have inside a jelly form liquid full of particles, the ions, molecules, and outside as well. So the ions can go through the channels inside, outside. But we're gonna see what is the reason, even though they are very long, they do not buckle. Those are naked axon, and those are with myelin. So I'm going to give you a mathematical model for a general axon, and it is just a curve in three-dimensional curve. Okay, this curve can be anything, but we can use Fenner-Serre coordinate, which I am sure you are familiar, introducing three unit vectors. T is tangent to the curve, N goes toward the normal. In fact, N shows the direction of curvature, and we have another binormal vector, B, which shows the direction of torsion of the curve in the space. So if we parameterize our curve by its arc length, these are what everybody in geometry knows. So these are also the connection between T and B, tangent, unit vector, normal, and also binormal. As I said, N shows the direction of curvature, and then B the direction of torsion, and this T is the tangent to the curve itself. And here you can find what is the relation. For instance, dTds is just, as you can see, K times N. So K here represents the curvature, and torsion. So here is the standard definition of curvature and torsion for such curve, which is parameterized by arc length. And these primes are with respect to S.
What is S?
S is the arc length. Yes. This is natural parameterizing of curve.
It's like a 5 pound.
Yes, but it is arc length.
Arc.
Yes. So now, but that was a curve in three-dimensional space. We, our aim was to give a model for the axon. This is just part of the axon. And now the surface of the axon we can introduce in this form. Alpha itself is the curve. We have two normal directions to t, and we just add two unknown functions, one in n and the other in b direction. Which when you add together, you can build up whatever function in the fiber form that you want. So this is exactly the starting point, and this is the surface of the axon, which is the membrane. Now, as Daniel in the morning said, and also Nilufar, intrinsically, the metric tensor gives you information about the membrane or the surface, and the definition are very standard. Just you see them here, and we can find them based on the very general, definition. And these are our E, F, and G. So that phi, we have also phi here. S is just the arc length. If we take here to be 0, then it means how much you go on the curve. But phi is an angle, which very soon we will see that this phi is measured from a reference direction, which is n. Anyway, so after we found our intrinsic property of the surface, we may talk about its extrinsic property, which is, of course, before I go to that end, everybody also knows that the surface element is given by this square root of gt st phi. These are our parameters. This is the surface element on the axon, and as you see here, the surface element depends on tau as well. So we expected to have k, but now we also have tau. Now I introduce n, which is the normal direction to the surface of the axon, and usually it is defined by using the definition of the surface. So this is its definition. We have two parameters, phi and s. So when you find the cross product, and in fact these are the things you call u1 and u2 in your calculation today. Anyway, we found n. N is just a general unit vector, and it has all components in t, n, and b direction. So as I said, this is a model, mathematical model for the axon, the surface of the axon. And now, after we have n, we can find extrinsic curvature. So extrinsic curvature definition Mr. Daniel gave in the morning. And now we can find them. Oh, of course, the exact form of Kij is like a train. So I prefer not to give here, but what is our aim to go at the end? We're going to find Gaussian curvature K and total curvature H, which I said at the beginning. If the fiber or the surface buckles, these two, they are not finite there, so they diverge. So our aim is to find K and H, as I said. And again, for the general case, it is very complicated, so I divided into parts. First, let's consider the axon is circular cross-section. So circular doesn't mean it is a constant circle, but it is it can be also variable cross-section, but circular. So this is how we can introduce circular cross-section. And as you see here, R is a function of S. And after you put it down, by the way, the cross-section, the radius of the circle is RS. So it means that depends on where you are, based on S, R change. And the K and H, they are here. So now, RS, as I said, is general. If we just look at the case when RS is constant, but we have still K curvature and torsion. What happens? K and H become very, of course, simplified, and this omega is just given here. Tau didn't appear in K and H, so it means that when the radius is constant, then tau has no contribution in H and K. But still, we have a problem here, which is omega. As you can see, omega is R0 Ks cosine phi minus 1. So now phi is measured from the direction of normal n. So if K and H, omega is 0, K and H both, they diverge. So that is the point the nerve may buckle. So how we can check it out? When you just try to bend the axon, at these 2 points, angle phi b plus minus, we will have two points at which omega gets 0. And before that angle and after, we will have, of course, everything regular. But those 2 points, we will have a spikes, as Mr. Kundelman said. So now, if this was the case, we would say, okay, we have to put condition on R0K to be less than 1. If this is the only way that we can get rid of vacuum. So if R0K is less than 1, but this is what usually everybody thinks. Okay, if R0 is constant, because we know what is the radius of the axon, K, it means that you cannot bend the axon as much as you want. Eventually it will start to buckle. So in our body, but this is not the case. The reality is this axon, they pass through the passages which are not, in our hand. So they may need to bend more than which is allowed here. So then the question comes, so how they avoid not to buckle? And this is what I'm going to answer now. If RS is not a constant, so it means that the radius of axon changes, suppose. What happens? Our K and H I already found, I showed you, are these. If you look at denominator, we have a sin omega here, but in addition we have also R prime square. And these two together, they never get 0. You see, if R is a function of S, R prime is non-zero, and then this is never get 0. So then, in other words, there is no anymore any condition. So it can be bent as much as you want. So in other words, when axon should bend much, it changes radius, and beautifully, goes. This problem will be solved. But of course, we have R in the denominator, which we know R never gets 0, and R prime also. So this is when R is a function of S, it solves it. So now this is buckling, which I told you, when you just try to bend. Yes. And this is, let's say, one yearly conclusion. So if R is, as I said, constant, then R0 Ks should be less than 1, or R should be function of S. Now, the other case is if it is non-singular cursive, what will happen? So, non-singular means R is function of phi, something like this. So I didn't put S here, because if you put S also there, it will be very complicated. So suppose that R is just a function of phi. So this means the cross-section is not sequent. You see how complicated is the structure of K, and also H similar. But forget about the numerator. The numerator is simply as you see here. But this time, unlike the previous case, tau also appeared in the denominator. So it has some rule when it's not sequent. And now let's just discuss two cases. When torsion is 0, we can see that K and H are given by these two expressions. Do we have any problem here? Yes, we have. Still we have. If torsion is 0, we may have this to be 0, and then again it has the chance to buckle. So then we have to again say, okay, R top R should be bigger than 0, less than 1. So then, which is not in reality. So then we come to the case when torsion is non-zero. When torsion is non-zero, what happens? When torsion is non-zero, it never gets 0 again. So then, in other words, if R is not function of S, only phi will be enough, but this time there will be torsion. So the axon will change its space structure to avoid buckling. So now, when R is function of S and phi together, then definitely there is no going to be buckling, because from the previous case, it will be fixed. Now, okay, so we understood why. I answered already the question I asked on the title, why axon does not buckle. Now, okay, when they do not buckle, they bend. I mean, smoothly. The question, what kind of curvature they use? What kind of curve they use in fact? So now, our friend left, but I can say everything depends on K and H. So K is the Gaussian curvature, H is our total curvature. Here, I consider the simplest case, which of course when we go through the other cases, almost will be the same. Suppose that R is constant, and the condition R0Ks, kappa S less than 1 is satisfied. Then we don't have any buckling, and these are our K and H, and this is our surface element. Question is, okay, this axon bends in the space. What will be the function of the curve which axon bends upon? So now we come to the theory of what Daniel and Niloufar they introduced in the morning. This is the simplest, very naive theory or model, which works here perfectly. So we suppose that the energy which is involved here is just the bending energy. And even I didn't consider the spontaneous curvature, which already I said, this spontaneous curvature is usually considered by the other surface tension and also the gauge potential. So I only consider the bending energy to be proportional to H squared, which is our total curvature. When you put it down, we have H, we can just, and we have dA. You put it down, and you find a kind of complicated integral. You are sleeping. Last semester we discussed this kind of integral. You cannot, by real analysis, you cannot find it. So we have to use a complex variable to solve this integral, and it is doable, in fact. And when you find the integral is very simple at the end. And this E, which appeared here, is just R0K. Anyway, I found energy in terms of a single integral, which is on the curve. And now this is a functional, and we're gonna, based on what we discussed in the morning, we're gonna minimize it. So this is the curve. So, but clearly, there is no derivative of K. So if you use Euler-Lagrange equation, it gives you K should be constant. So in other words, Ks should be constant. So the curve used by the axon is a constant curvature curve in the space. Understood? If it was on a plane, I would say it's a circle. But now we don't know yet. So the question, at least partially we know the answer. Whatever happens to the curve is just constant curvature. So the issue is what we have. So you were using the morning and the other day. I said it's so we have. Suppose this is our axon coming to a point which it should bend up and come out from here. So this is the going and this is the coming direction. So now we know the axon needs to bend here. So and we also know that the bending, of course, this is in 2 dimensions. I'm also talking about the plane curve. If it is plane curve, we know that the curve also stays in this plane, and we know it's a circle. So the circle is gonna go from here. Of course, this is our initial curve, and it will go up to here. But is there any circle passing through these 2 points? And of course, at these 2 points, it should be differentiable. So it means that it's derivative of the curve in both sides should be the same. So you cannot just draw a circle here. That's not the case. What happens? What axon does? In fact, here if you draw a normal line, and here also, if this will be of course, the radius of the curvature, the circle. So if they're the same, you can say, okay, this will be the circle. But if they are not the same, what happens? Axon from the side which is smaller extends a little bit more, and it comes up to here. So then, such that, I mean, in both sides maybe, then these they become the same. So then that curve will form there. But that is not the end. So the axon, the thing we know, the direction of outgoing and incoming, they are known. But we don't know where the bending starts and when it finishes. Only we know that they should be smooth. So anyway, we now understood that in one direction or both directions it may extend such that at the end a common circle will come up. But as you know, if you find one circle here, you can find infinite number of circles they satisfy. So it could be somewhere here also. So which circle they choose? So that is another question we're going to answer. You understand what I say? I mean, you can find infinite number of circles which they go smoothly from one to the other. And the answer comes from here. We find the energy. Okay, we understood that K should be constant. So this is the energy. But the energy is, energy depends on S, which is the arc length of the curve, and also its curvature. But we know that the curvature, K and arc length, they are related. And that relation is just, if you know what will be the final direction, you can know that this angle, which is the total bending, multiplied by the radius of curvature, gives you the arc length. So therefore, this S is not random. And in fact, S and K0, they are related. And the relation is, as I wrote here, and when you just put it down, you will have energy as a function of only rho, which rho is the radius of the curvature. In fact, inverse of K0, kappa 0. So when, as we know, the energy is going to be minimized, so we have now a function, not functional anymore, a function of rho, and we're going to minimize it. So we do it. We just take the derivative with respect to rho and make it 0. And then what's happening? We found rho to be a square root of 2r0. And it gives you, do I have time? No. Okay.
Yes.
So we found what is the radius of the curvature, which is exactly a square root of 2r0. r0 is the initial radius of our axon. So therefore, for the plane axon, which means the both parts of the axon, they are on the plane, they are connected by a curve with curvature, radius of the curvature to be a square root of 2r0, which r0 is the initial radius of that. So now what this is when it is on the plane. Suppose one of them is not in the plane. So in other words, suppose that this is the axon coming and the other one going like this. What will happen? So they are not in a single plane. This time we know the curve goes from one to the other is constant curvature, and what constant curvature we know? The simplest constant curvature in the space is helix. So that is exactly the answer. Helix is the answer. So, but same problem we still will have. We will the helix starts from one and ends up with the other. But the smoothness of the axon, which we discussed, constrained our helix. And the question is, what helix will fit these two branches? And this is what I answered here. So helix is its definition is here given, and helix has torsion and also curvature. These R is these are circohelix, of course. This the radius of the circle of the helix, and as you see here, S is also our arc length. They are related, of course. Now we can find the energy of the the curve part, and exactly in terms of what we have. We have theta here. In previous case we had psi, and theta is the space bending of the curve. but still it's constant. So when you try to find the stationary energy, you just need to take the derivative of E with respect to, here I introduce epsilon to be the ratio of tau over kappa, torsion over curvature, and what it gave me is this. Epsilon is equal to 1 over 3. Epsilon is, as I said, tau over kappa, 1 over 3, 1 plus r0 square over r square minus 1. And this is exactly the helix will fit into our junction. And now if you put epsilon to be 0, which means the torsion is 0, we go back to previous case, and exactly same result will come out. So in short, we found, first of all, why mathematically these axons are very long fibers, they do not buckle. Then also we discussed if they don't buckle in bending, what kind of curve they use to go from one branch to the other, in both in plane case and also in space curve. So this was my talk. If you have any question. So let me add some very simple stuff. I asked if it buckles, what happens? As our biologist in the morning said, these axons, they carry the electrochemical signals on one side to the other side of our body. So this happens through an equation. It's called equation of cable. And that equation is formed based on the structure of the axon's, membrane. We have plenty of, infinite number of channels, ion channels, which in certain time they open. And as biologists say, they say axon is like a salty banana. So banana, inside we have potassium, rich for babies. And outside, when you put salt, sodium is outside. So this is the structure of axon. So in certain time, especially when they are the action potential is formed, these channels they get open, but sequentially. So the signal goes through the channel, the axon, very beautifully. As I said, the cable equation is for that case. But the question is, the problem is when the axon buckles, the structure of the membrane changes, and definitely if such axon is going to take the signal through, we will have problem. And this, in fact, when a trauma happens in our brain, so the axon start to swell, and that time we may have such kind of buckling due to the time. I'm sure when you wait for enough time, they may not be anymore, but in short time, and that may cause problem for those people they got the trauma. So that is why we know in healthy brain, on a healthy neuron cell, there is no buckling. Otherwise, we wouldn't behave, as we do.
Normal.
Yes. Okay, so.
Okay, thank you.
Yes.
You said in the beginning that the nerve cells do not buckle if R is a function of S,
Yes.
but you didn't specify any form of the function. Does it
In
have
fact-
to be there has to be a
I worked on, in fact, but it was very short time, so I didn't put here. There are models again. We have to follow the model we discussed in the morning. Any other form, it should satisfy the minimum energy, bending or electric energy, it doesn't matter. And then we find it. But it may not be very easy.
But some functions at least should be excluded. Maybe some should be or as a function of S, but when is the function of S?
This lady, Niloufar, shown a function in the morning, if you remember, and that is exactly a good candidate. The reason is the myelin, which they force the axon, that's another reason that you see the deformation. Yeah, that part which myelin is there, okay, it's quite, longer than the node. So that node may, a little swell, and that is exactly the form she shown. So all, in my view, by this theory, they should satisfy the minimum energy, bending energy at least. And then you find exactly what is the form.
It's not any function.
No, it's not any function, definitely. Okay, thank you very much.
Okay, thank you.